Our proposal is about an Ethereum blockchain that explicates and ensures design-level safety properties for smart contracts. The current contributors include Nikolai Buellner, Shuo Chen, Yang Chen, Zhongxin Guo of Microsoft Research, Pen Liu, and Nanqing Luo of the Penn State University. We stand at the edge of decentralization revolution. There is a major obstacle to overcome. Smart contracts do not have enough transparency and trustworthiness. They suffer from the unintentional vulnerabilities and logic trapdoors. There are numerous high-profile incidents that have resulted in significant financial losses. This issue is compounded with the code is law tenet in blockchain, so the losses are irreversible. Conventional smart contract verification and auditing are very helpful, but their focus is to find as many vulnerabilities as possible only in the development and testing phases. Our proposed technology is called Theorem-Carrying-Transaction or TCT. The goal is to enforce design-level safety properties that explicitly express intended behaviors of contracts, which are enforced at runtime. With TCT, every transaction must carry a theorem that proves its adherence to the specified safety properties in the invoked contract. The blockchain VM ensures the validity of the theorem right before executing the transaction. The uniqueness of the idea is it combines the benefits of runtime checking and the symbolic proof. In TCT, every theorem is about a straight line code, so it is much easier to prove. In addition, once a theorem is validated by the blockchain, future transactions can reuse it to affirm their safety. Let me explain why design-level properties are the key to the trust of smart contracts. First, what does trustworthiness mean? Conceptually, it means that a system behaves according to its design specification, but in reality, it is often reduced into a matter of enumerating specific low-level violation patterns. Bugs are often attributed to programmers' failure to expect every unexpected possibility. So this is paradoxical. Trust is hard to establish if the focus is on the program's non-intentions rather than intentions. Smart contract security is in the same situation. For example, integer overflow and reentrancy are two separate low-level patterns, often described as representative security bugs. In fact, integer overflow is not a bug per se. For example, the Uniswap code intentionally uses integer overflow. And reentrancy is not a bug either. It is basically a synonym of callback function, which is common in real-world software. We advocate design-level properties because they will free programmers from the burden and the risk of enumerating low-level bug patterns. Now, imagine that time travels back to the year 2016 and a programmer needed to write an ERC20 token contract. And back then, nobody knew about the bug patterns exploitable by integer overflow and reentrancy. So what could be done to make the contract secure? It turns out that if the following design level properties were specified and enforced, the attacks would not succeed. The properties declare that all balance amounts are non-negative and the sum of them should equal total supply. These are simply the programmer's design intentions, assuming no knowledge about low-level details. Trust concerns are not only about vulnerable contracts, but also malicious contracts. There are many meaningful design-level properties which can bolster users' confidence. They often require symbolic reasoning because concrete checking is infeasible or too expensive. For example, a property may contain quantifiers, map and set operations. It may contain real number equality with infinite precision. It may talk about a relation under a hypothesis. It may talk about a relation between encrypted variables as if it was from God's perspective. Also, it can use a modifies clause to declare that no variables except some specific ones can be modified by a function. All these properties are difficult to check concretely. TCT is capable because it relies on symbolic reasoning. Another point I want to make is that TCT enables behavioral subtyping. Behavioral subtyping has been an aspiration in the OOP community for decades. It ensures that inheritance implies conformance. For example, we may build this class hierarchy for ERC20 tokens. Once safety assertions are added into the base class, people can easily trust that all descendant contracts are safe. This would be ideal for trust and security. However, with today's conventional subtyping, inheritance doesn't imply conformance. The well-known example is the square and rectangle enigma. So this assertion is true for the base class rectangle, but because the rectangle variable holds a square object, which is of the derived class, this assertion actually fails. It is known that ensuring behavioral subtyping is difficult by static verification, but I will explain that it is natural for TCT. Our vision is to build an Ethereum-compatible blockchain called TCT ETH. It can execute all existing smart contracts, and more importantly, it can execute new contracts that contain assertions of design-level properties. The decentralized trust assumption remains unchanged, whether it is POW, POS, or POA. We envision several changes for the future of smart contracts. First, spec is the law of code. Programmers use formal specs to confine the code's behaviors. Ideally, a user agreeing on the contract will only mean that he or she agrees on the spec. And second, programmers' focus will be more on writing assertions, resulting in an increased assertion to code ratio. And behavioral subtyping will become a collaborative effort of all abstraction levels, such as the ERC standards, libraries, and individual contracts. Also, there will be a clearer business interface for code auditing. The client provides the code and the initial spec, and the auditing company defines the final version of the spec and delivers proven theorems. With the vision, let's talk about the technology itself. TCT is motivated by two technologies. The first is proof carrying code, or PCC. The goal is to ensure safety properties of third-party kernel extensions. With PCC, the extension provider bears the responsibility to provide a safety proof, and the kernel only needs to check the proof. This is more practical than requiring the kernel to prove the properties. Another technology is concolic testing and fuzzing. The word concolic combines concrete and symbolic. A program is executed and the concrete chase is recorded. The code chase is symbolically analyzed by a constraint solver. The goal is to generate the next input that is guaranteed to result in a different code chase. For example, in this code, the security violation is hidden very deep for random fuzzing, but symbolic fuzzing can easily trigger this bug. A great number of bugs in Microsoft Windows and Office code have been found by this technique. Here is an example to explain our technology. It is a token contract containing the patterns of integer overflow and reentrancy. I assume that you are familiar with them. In attack 1, the attacker issues this transaction with big values in these two arguments. Interestingly, the execution does not trigger any exception, but the balances of these two accounts become enormous. In attack 2, suppose the balance of the attacker is 5. When the attacker calls this function, it triggers a reentrancy pattern. If it repeats 10 times, another account of the attacker will get balance 50. Now, let's prove a theorem about the first transaction. The red is the invariant I mentioned earlier. The programmer may express her intention in this blue hypothesis, phi vs. V represent the input arguments and S represent the blockchain state. This hypothesis states that total supply, underscore value, and underscore fee should all be between 0 and 2 to the power of 255. The theorem is that, under the hypothesis, the code chase should maintain the invariant. This theorem can be represented as this boogie code. In the beginning, it assumes the hypothesis and the invariant. In the end, it asserts the invariant. Of course, we need some axioms for the math operations. Then the boogie verifier can successfully verify the code, meaning that the theorem is valid. The general form of the theorem tau is like this. F is the entry function of the transaction. Phi is the hypothesis, as I explained. H is a hash value that uniquely represents the code path. We call it path hash. The theorem means that for any transaction started by invoking F when phi is satisfied, when it is completed and the hash of the code path equals H, then all assertions along the code path are guaranteed to hold. Now let's see the reentrancy attack. The invariant is the same. Theorem tau is this. Note that the code hash is this one, which corresponds to the path that repeats the add operation 10 times due to reentrancy. Again, imagine time travels back to 2016 and the programmers were unaware of the reentrancy pattern. But this would be okay because it was the attacker's obligation to come up with phi vs and prove the theorem. The attempt would be doomed to fail. The TCT protocol involves three parties, exactly like today's situation. There is a transaction issuer, such as a wallet. There is a pre-execution service, such as Infura.io. It is basically an Ethereum node with public web API. Then there is the Ethereum network. In TCT, however, every node has a theorem repository. Let me walk through protocol workflow A. First, the issuer generates a transaction Tx equals f of v. For example, this can be the transaction. The transaction is sent for pre-execution, and the pre-execution service tries to find an applicable theorem for the transaction. But in this case, there is no such a theorem, which means the issuer needs to provide and prove a theorem that is applicable to the transaction. So the issuer provided theorem tau and represent the proof as rho. It sends Tx, tau, and rho to the blockchain. The blockchain test runs Tx to record the trace, and it rejects if the passhash does not match. Then it checks if the proof rho is sound. If it is, then theorem tau is added to the repo. It also checks if tau is applicable to the transaction. If it is, then the transaction is executed. Now, suppose another issuer generates a different transaction with value 20 and fee 2. This time, the pre-execution service finds an applicable theorem tau. In this case, the issuer simply submits Tx and tau. The blockchain confirms that tau is in the repo and execute the transaction. The runtime overhead is minimal. As you can see, the theorem is very general. It can be used for most of the normal transactions. Workflow C is for a programmer of the contract to submit theorems during the testing phase. The only effect is to populate the theorem into the theorem repo. The transaction is not actually committed to the blockchain state. In reality, we expect most theorems are accepted by the blockchain via workflow C because the contract programmers are supposed to run test cases that cover all normal scenarios they can imagine. Most real user transactions go through workflow B because most transactions are expected to be normal. Workflow A only happens when a real user issues a transaction that goes through a code path unseen in all test cases. It is likely an attack. If it is not an attack, the user unfortunately needs to take the burden to provide a new theorem. Besides token contract, we consider Uniswap as a more compelling showcase, and we have done some homework. The individual token contracts are already exciting since they are a major application scenario for Ethereum. But Uniswap is a decentralized exchange. It implements a market for people to exchange tokens. It is one of the most used systems in Ethereum. If you follow the FTX scandal, you know that lack of transparency allows centralized exchanges to arbitrarily manipulate client funds. Therefore, an important value of decentralized finance is to promise much better transparency. As I said in the beginning, the code being public doesn't mean good transparency due to bugs and trapdoors. TCT can improve transparency. This slide explains Uniswap automatic market maker algorithm at the design level. It is a dynamic mechanism to decide the relative price between a pair of ERC20 tokens, AAA, and BBB. There are two types of investors, liquidity provider and trader. A liquidity provider can only move the black dot along a straight line, and a trader can only move the dot along a hyperbola. All these transactions interleave, and the price can reach an equilibrium. There are good online resources to explain the rationale of the algorithm, but those are not of TCT's concern. The concepts at the mathematical level are clear, but TCT is about smart contract code. It is much more complex. Every transaction involves at least 5 contracts. Note that any company can develop a contract as Uniswap periphery. And these contracts can be any ERC20 contracts, including ones that have not been implemented today. And this resonates to the previous discussion about behavioral subtyping, like the rectangle and square enigma. Essentially, we want to assert some properties before the derived classes are implemented. This slide shows some design level properties. We can define properties to assert that LP's transactions are safe, traders' transactions are safe, and other meaningful properties such as all the pools are independent from each other, etc. The purpose of this talk is to call for collaboration. Our first milestone is to demonstrate a testnet of the TCT ETH blockchain along with the TCT-capable browser wallets and pre-execution service. They speak the TCT protocol. In this testnet, we will demonstrate the TCT-enhanced Uniswap contract to trade ERC20 tokens. We need expertise in several areas. First, Ethereum. We had some expertise in our previous project called Forerunner. It has already built the functionality to record concrete EVM code paths and applied optimization techniques to it. The second area is Solidity and EVM. For Solidity, we may consider the Solidity metadata feature to specify contract and function properties. For EVM, we will need an EVM symbolic checker like Helmos. About formal verification, our first stage tries to use Boogie. As the project moves into next stages, we may use these three directly, implement theorem generation algorithm using Farkas lemma, separate proof generation and proof checking, etc. Also, we need the expertise on wallet and pre-execution service. We realize that a community is crucial to the success. We want partners who genuinely share the same vision and passion, who have the expertise to contribute, who want to make a generous amount of commitment to this partnership. An incentive is an important mechanism to form a successful partnership. But we admit that this is an area where we currently lack experience. We think that TCT may provide a new business incentive model for stakeholders around smart contract audit. TCT is an open project. Programmers can contribute at the EVM and Ethereum level and at the smart contract level. Partners can contribute blockchain nodes for the testnet, and organizations can also fund this project. And finally, you can also contribute community building ideas. This is just the beginning, so many ideas are not concretized, but I hope you share the same vision and consider contributing to this project. Thank you very much.